This first series have been taken from the 6D transition series. The second series from atomic number 90 to 103 they have taken from the 7D transition series. Interstitial compounds mean when there is a space or vacancy in some solid, in that metal can be inserted. So due to this electron-electron repulsion, it will cause the expansion of electron cloud. So here the atomic radii will be keep on increasing. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Today I am going to start a new chapter, that is D and F block elements. For this chapter, the marks overall weightage as per the last year, we have 8 marks. Total weightage of this chapter is 8 marks. So in this session, what we are going to discuss means introduction for D and F block, and how do you define or how do you classify as transition series, general electronic configuration of D and F block elements, characteristics of transition elements and trends in property. Some of the trends we will study today in this session, and remaining introduction, transition series and electronic configuration and characteristics of transition series will study. In the modern long form periodic table, the elements have been grouped into 4 blocks, namely. We know that in the modern periodic table there are 4 blocks, that is S, P, D and F block. Those elements belonging to those blocks will be called it as S block elements, P block elements, D block elements and F block elements respectively. Okay. But the elements belonging to groups 3 to 12 are called D block elements or transition elements. The group number we know that rows will call it as periods and vertical columns will call it as groups. Those groups, in that number we are also having 18 groups. From the group number 3 to group number 12, that middle portion of the modern periodic table will be considered as D block elements or transition elements. So why we will call it as transition elements for D block elements means because it is having some transitional property and it belongs to some of the properties of S block elements and also it belongs to some properties of P block elements as well. So the D block elements will be considered as transition elements. The elements which possess partially filled D subshells either in the atomic state or their oxidation state are called D block elements. Here the elements which possess partially filled D subshells either in the atomic state or in the oxidation state. This is the overall periodic table. Okay. From group 3 to 12 will considered as D block elements, okay, or transition elements. In the group 6 and 7, that is from after atomic number 57, that is 58, and after atomic number 89 it is 90. See here last 71, after that 72. Okay, means this first series have been taken from the 6D transition series. The second series from atomic number 90 to 103 they have taken from the 7D transition series. Okay. And that's why these two series will call it as inner transition series or F block elements. Because they have taken from inner side of the transition series, I have been called for inner transition series or F block elements. These two are F block elements. Okay, the first line will considered as lanthanoids because the first element is lanthanum, and the second series will considered as actinoids because the first element is actinium. Okay, and this is the 4F and 5F series. This is about the overall picture of D block elements and F block elements and where it has been placed in the modern periodic table. Next, transition series. The d-block elements are called transition elements as they represent change in properties from most electropositive s-block elements to least electropositive p-block elements. As I told, why the d-block element has called as transition elements, because it possesses the properties of elements of s-block elements which is more electropositive in nature, and it will possess the elemental properties of p-block elements which is most electronegative in nature or least in electropositive in nature. So that transitional property will call it as transition elements. Copper, silver and gold are transition metals because in their commonly occurring states they have partly filled d subshell. Zinc, cadmium and mercury of group 12 do not have partly filled d subshell in their elementary state or commonly occurring oxidation state, and hence are not considered as transition elements. Here copper, silver and gold are transition metals because they are partially filled d subshell, and zinc, cadmium, mercury of group 12 do not have partially filled elements in their elementary shell, so they does not considered as transition elements. Transition elements consisting of 4 rows. These series are called transition series. The 4 rows of D elements will be considered as transition series. 3D transition series, the transition elements with atomic number 21 to 30, that is scandium to zinc, will be considered as 3D transition series. Having incomplete 3D orbitals is the first transition series. Here D orbitals will be not completely filled. Next 4D series, it consists of element with atomic number 39 to 48, that is from yttrium to cadmium, having incomplete 4D orbitals. Here also D orbitals have been not completely filled, and that will be considered as second transition series. And next 5D transition series, it consists of element with atomic number 57 to 72 to 80, because here there is a break, you know that. So 57 lanthanum, and next 72 hafnium 2, that is mercury, and next it is also having incomplete 5D orbitals, and that is third transition series. Next 60 transition series, it consists of elements with atomic number 89 actinium to 104 rutherfordium to 1112, that is beryllium, because that element has not been discovered yet. So having incomplete 60 orbitals, it is called fourth transition series. Okay, these are the 4 transition series. Next one, general electronic configuration. See here, the electronic configuration, you know that N-1 D, N-1 D, 1 to 10, NS 1 to 2. Okay, what is this N-1 means? Penultimate shell. Okay, what is that? N-1, that is penultimate shell. The electrons which will be entered in the last orbital is, that is penultimate shell, means last but first shell. Okay. For example, if we take manganese, that is atomic number 25, what is its electronic configuration? 1s2, 2s2, 2p6, 3s2, 10, 12, 3p6, 4s2, 10, 20 and 3d5. Okay, this is the manganese atomic electronic configuration having the atomic number 25. Okay, see here 4s is the outermost electronic shell, but it will fill first rather than 3D orbital. Okay, the last but first shell will be filled. Later, the innermost electrons will be filled. And these are all inner shells, no problem. But 4s is the outermost shell, then third orbital, but it will fill up first and later the last but first will fill. So that kind of orbital will call it as penultimate shell. That's why here N-1. And remaining electronic configuration we can see here. Scandium atomic number 21, 3d1, 4s2, titanium 22, 3d2, 4s2, Next, vanadium 3d3 4s2, chromium 3d5 4s1, manganese 3d5 4s2, iron 3d6 4s2, and cobalt 3d7 4s2, nickel 3d8 4s2, copper 3d10 4s1, zinc 3d10 4s2. The first the outermost electrons have been filled, later the inner electrons have been filled. Okay, that is the meaning of penultimate. That's why its electronic configuration is n-1 into d to the power of 1 to 10 electrons and ns into 1 to 2. Overall, d shell is having 5 orbitals and each orbital will contain 2 electrons. The capacity of d shell will be having 10 electrons in its shell. Okay. Next, general electronic configuration of d block elements. First transition series 3d series, atomic number 21 to 30, 3d 1 minus 1 to 10 and 4s2. 4d series, atomic number 39 to 40, 4d 1 to 10 into 5s2. Third transition series 57 to 72 and 72 to 80, that is 5d, xenon 5d1 6s2. In the F block elements, we will introduce here F series, that is F 1 to 14 into 5d into 1 to 10, 6s into to the power 2, and 4 transition series 89 and 104 and 112. Okay, 89 here radon 61 into 7s2, 104 to 112, here also F series have been introduced. So 5f14, 6d 2 to 10, 7s2. Okay, that is how the general electronic configuration of both d orbitals, d block elements and f block elements. Next, characteristics of transition elements. Except for mercury, which is a liquid at room temperature, all other elements are solid metals exhibiting all the characteristics of a metal except mercury. About mercury, we know that is an exceptional case. In the room temperature, it will be in liquid state, and other elements, that is in the transition metals, we know already we are calling as metals. So metals usually it will be solid in nature and exhibiting characteristic of a metallic nature. They show variable oxidation states unlike a SP, S and P block elements. S block and P block elements are having different kinds of oxidation state and little bit constant oxidation state, but in the D block elements it is having variable oxidation state. So +5, +6, +7, like that various or variable oxidation states you can observe. There are some of their compounds show catalytic properties. You know what is catalyst? It will be used in the chemical reaction to enhance the rate of a reaction. So that catalytic properties will be shown by the some of transition elements. Those elements are platinum, palladium, like that, vanadium. These are the elements which are present in transition elements and they show majorly catalytic properties. Their compounds are colored. Okay, the compounds are colored. You have seen in the laboratories there are so many colored compounds. They are due to from the colored nature of transition elements like manganese, chromium or any gold. So that kind of colors you can observe. They have great tendency to form complex compounds. Okay. The D block elements have the capacity to form complex. Next, they form alloys and interstitial compounds. The mixing of metals will call alloys. The elements in D block elements have that property to form alloys and interstitial compounds. Interstitial compounds mean when there is a space or vacancy in some solid, in that metal can be inserted. That metal will be called it as interstitial compound. So overall, in that vacancy, that metal can be included or inserted. These are the major characteristics of D block elements. Usually they are hard or solid in nature. They show variable oxidation states and they are having catalytic properties. They are colored and complex forming, alloy forming and also interstitial compounds forming elements. Okay. Next, general characteristics of transition elements. Usually how it will form the atomic radii, ionic radii, oxidation state, like that we'll discuss one by one. And we have to understand before going to the general characteristics of D block elements. We know that in the S block elements there is a one trend which it is following, and in P block also it is following one trend according to its property. But in transition series it follows the properties of S block, it follows the properties of P block. So you cannot see the gradual increase or gradual decrease in its property. It is having so many variations. So why that variations will happen, how it could be explained, those things we'll see one by one. First we'll see the atomic radii. Atomic radii means, you know, the distance between nuclei to outermost electron, we'll call it as atomic radii. The atomic radii of the elements of a given series decreases with increase in atomic number, but this decrease becomes small after midway. Means when increase in atomic number, the distance will become decreased. Okay, till what it will be present this trend, till the midway it will follow, and later that will be changed, the trend will be changed. Once again, the atomic radii of the elements of a given series, atomic radii will be decreased when the increase in atomic number will be seen. But this decrease becomes small after midway. In the first transition series, the atomic radius gradually decrease from scandium to chromium. From scandium to chromium, the atomic radii will be gradually decrease. Thereafter, it is nearly the same. Okay, see here, from scandium to chromium, the atomic number will be decreased. Later, it will be the almost same. Next, why it will be happen like that? In the beginning of the series, the screening or shielding effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases. Hence, atomic size radius decreases. In the beginning, shielding effect on the d electron is not that much effective. So, the nuclear charge and the outermost electron will be having the strong electrostatic force of attraction. So, it keeps on decreasing. After some time, it will not show that much of, or it will start showing the screening effect much. So, it will not decrease as we have seen from scandium to chromium. In the middle of the series, increase in the nuclear charge and increase in screening effect balance each other. After the chromium, what will happen? Increase in nuclear charge, increase in screening effect or shielding effect. So, both the energy or both the effect will balance each other. So, it will not show any decrease or increase. So, atomic radii become almost constant. Increase in atomic radii towards the end is due to the electron-electron repulsions causes the expansion of electron cloud. Later, increase in atomic radii towards the end is due to the electron-electron repulsion. We know that electron is having negatively charged and another electron is also a negative charge. It will start repelling. So, due to this electron-electron repulsion, it will cause the expansion of electron cloud. So, here the atomic radii will be keep on increasing. Okay, this is the reason from scandium to chromium, screening effect will be not that much effective towards the and nuclear charge and outermost electrons will be having strong electrostatic repulsion. So, atomic radii will be increased. After that, the charge will keep on increasing, nuclear charge, and also outermost electrons will also keep on increasing. The effect will be balanced each other. So, atomic radii for some reason it will be constant. Later, increase in atomic radii due to the electron repulsion and expansion of electron cloud. This is the reason how or why atomic radii will be decrease or increase in D block elements. The atomic radii increases while going down in each group. We have seen from left to right first. Now we are seeing from top to bottom in the group. The atomic radii increases while going down in each group. However, in the third transition series from hafnium and onwards, the elements have atomic number nearly to equal those of second transition series. From top to bottom, almost after the hafnium onwards, the equal to the second transition series, the atomic numbers are present, or atomic radii nearly it is present. So, it is keep on increasing. Reason, this is due to the introduction of an additional shell at each electron, each new element down the group. Nearly equal radii of second and third transition series elements is due to a special effect called lanthanide contraction. Here we know after one group or one row that new additional shell will be added. So nearly equal to second and third transitional series will be present, and there is a special effect called lanthanide contraction. Due to that, atomic radii will be increased. See here example, that is zirconium 160 picometer and hafnium 159 picometer, molybdenum 146 picometer and tungsten 139 picometer. Okay. Next, technetium 136 picometer and rhenium 137 picometer, cadmium 154 picometer and mercury 157 picometer. Here due to the lanthanide contraction, you can observe the special effect. This is the increasing atomic number, and see scandium to chromium, it is keep on decreasing. Later it keeps on constant for some time and later it starts increasing. Same here in the lanthanum to tungsten and little bit constant and later it will be increased. Okay, this is the atomic radii and this is increase in atomic number. Next is ionic radii. The ionic radii follow the same trend as the atomic radii. Okay, little bit same as atomic radii. So it will follow the same trend as atomic radii. For the same oxidation state, the ionic radii generally decreases as the atomic number increases. When the atomic number increases, decrease in the ionic radii in the particular transition series. For the same element, the ionic radii decrease with the increase of charge on the ion. For example, radii of some ions are given below. Here Fe2 plus 76 picometer, Fe3 plus 64 picometer. Here charges will be different, so picometer will also get different. Nickel 2 plus 72 picometer, nickel 3 plus 62 picometer, manganese 2 plus 80 picometer and manganese 3 plus 66 picometer. Okay, when the oxidation state increases, decrease in ionic radii. This is what we have to understand here. Later, density. All metals have high density. Within a period, the densities vary inversely with the atomic radii. Densities increase along a period. Also, densities increase upon descending down the group. All the metals have high density and within a period, densities will keep on increasing and it will be inversely proportional to atomic radii. Densities increase along a period and also density increases upon decreasing the group. Reason, the atomic volumes of transition elements are low because electrons are added in n-1 d subshell and not in ns subshell. Usually atomic volumes of transition elements will be low because the last electron will be entered in the penultimate shell, that is n-1 d subshell, not in ns subshell. Therefore, increased nuclear charge is partly screened by d electrons and outer electrons are strongly attracted by nucleus. Moreover, electrons are added in inner orbital, consequently densities of transition metals are high. So, the inner electrons will only having the it will be high densities and the outermost electrons will be having strongly attracted by the nucleus. So, its density of metals will be high. Next, trends in properties of transition metals of first series. In the first series, we will see the some of the other properties. First one, metallic character. All the transition elements of first row are metals. From scandium to zinc, almost all the elements are metals. They exhibit typical metallic properties like metallic luster, high density, high metallic and boiling point, malleability, ductility, high tensile strength, hardness, brittleness, high thermal and electrical conductivity. Since it is a metal, these are all metals from scandium to zinc. They show lustrous, means shining. They are hard, they are solid in nature and they have high density, high boiling point and melting point, ductility, malleability. Malleability means that metal can be drawn into thin sheets. Ductility means that metals will be drawn into thin wire-like structure. So those are malleability and ductility, high tensile strength, brittleness, hardness, electrical conductivity it can possess or it can conduct electricity, and thermally also it can conduct. These are the general properties of metals and which can be expected from the first transition series also. They exhibit all the three types of structures: cubic closed packed, that is CCP, or face centered cubic FCC, and hexagonal closed packed HCP and body centered cubic BCC. Okay, they will show or they exhibit all the solid structures like HCP, BCC and FCC. These are the various types of cubic centers. Here individually scandium will show HCP and BCC, titanium HCP and BCC, vanadium BCC, chromium BCC, manganese HCP, iron BCC, cobalt CCP, nickel CCP, copper CCP, zinc HCP. These are the individual metals which show or it will show the what kind of cubic centers. Next, ionization enthalpy. The ionization enthalpy increases in this series as the atomic number increases. When the ionic enthalpy is increased as the atomic number increases. When atomic number will keep on increasing, ionization enthalpy will also keep on increasing. However, the increase is not regular. This is because the effect of increasing nuclear charge is somewhat neutralized by the increasing shielding effect of 3d electrons. As the atomic number increases, that ionization enthalpy will also increase, but in transition series it is not regular due to increasing nuclear charge, and it will be neutralized by the increasing screening effect by 3d electrons. After some time, nuclear charge will increases. By the same time, the 3d electrons shielding effect will also increase. By that time it will get neutralized. So, increase in atomic number will not show the property of increase in ionization enthalpy after some time. In a period, the ionization enthalpy increases from left to right. In the period left to right, ionization enthalpy will increases. For example, the ionization enthalpy values for scandium, titanium, vanadium and chromium are fairly close to one another. From scandium to chromium, fairly close to one another. See here, 631, 656, 650, 652. Okay. Similarly, the values of iron, cobalt, nickel and copper are almost similar. Iron, cobalt, nickel and copper almost similar, 762, 758, 737, 745. Okay. First and second ionization enthalpies of 3D series elements, it will be measured in kilojoule per mole. The slight variations which occur in these values are mainly due to the slight changes in atomic radii. Slightly changes, if you see here, it can be observed by the atomic radii changes. The value of first ionization enthalpy for chromium is lower than expected. The first ionization enthalpy for chromium is lower than expected. This is because the removal of one electron produces extra stable d5 configuration. Because the one electron, whatever it is removal, it will produce as the d5 configuration. So, the first ionization enthalpy for chromium is lower than expected. The value of zinc is appreciable higher due to the additional stability associated with completely filled 3D level, that is 3D10 in zinc. The value of zinc is appreciable because it is completely filled, that is 3D10. The second ionization enthalpies of chromium and copper are unusual high because the electron is now to be removed from very stable configuration. That is chromium plus, which is 3D5 half filled, and copper plus, which is 3D10 completely filled. In the second shell, after removal of one electron, copper and chromium will become half filled or completely filled, so it will become highly stable. The value of second ionization enthalpy for zinc is comparatively low, as this involves the removal of an electron, which results in the production of zinc 2 plus having stable 3D10 configuration. Second ionization enthalpy of manganese is less than that of iron. This is because removal of second electron in manganese produces half-filled D5 configuration. Here, by seeing or by analyzing some of the elements in first ionization enthalpy and second ionization enthalpy is showing expected with a good result or with good values. How it will be related means, in the D shell, If it is completely filled, D10. If it is halfly filled, D5. Usually, electrons when completely filled or electrons with halfly filled, those show the stable electronic configuration. So, whenever it is completely or half filled, it will be in stable manner. So, that will be having more values. This is the introduction part of D block and F block elements with electronic configuration, general characteristics and some of the trends we have started. In the next session, we'll discuss about oxidation states and some of the other properties with its variations. I hope you have understood completely whatever I have taught in this session. We'll meet in the coming session. Till that, thank you.